So today we are looking at identities, inverses, and the determinants of 2x2 matrices. So your only maximum that you're ever going to ask to do manually of these things is with a 2x2. So just to recap, what do we mean by a 2x2? That is 2 rows, yeah, and 2 columns. Good. Okay, in scalar operations, one is the multiple identity. So what they mean by that, when we do scalar multiplications, okay, so when we're talking about an identity, it's when we times it by 1. So if we have scalar multiplication, that means if we're just using numbers and we go 3 times 1, what do you notice? We get the 3. We get what we multiply it by. So if we multiply something by a 1, which is like an identity, we get the same thing back, don't we? So if I said 4 times 1, I still get 4, don't I? Yeah? So the same thing is if you times a matrix by an identity matrix. So what is an identity matrix? If you have a look here, we normally use the letter I to indicate an identity matrix. And you'll see on the leading diagonal, there is 1s. So the leading diagonal means it starts in the top left-hand corner, yeah? And goes down. So you'll see that there's 1s, and everywhere else there is what? 0s. Now, can you notice this is a 2x2? So an identity matrix is actually, we call that a square matrix. Because you need the same amount of rows and the same amount of columns to have a square matrix. And you wouldn't be able to get a diagonal if it wasn't square. Yeah, that makes sense? So if you look here, this 3x3 is also an identity matrix, and we've got the 1s on that leading diagonal. So what we're going to do is show you that if you times something, a matrix by its identity matrix, you'll actually end up with the same matrix as you begin with. So let's have a look. So if we had A here, they're asking me to times the A matrix. So I'm going to write out A by the identity matrix. So the identity matrix for this one will be a 2x2 because I've got a 2x2. Okay, so let's practice what we were learning the other day with multiplying them. So remember we said we can do it because these two equal, and remember our answer will be a 2x2. Do you remember that? Yeah? So let's just write it out. So 2x2. So remember I said maybe just do the little boxes so you realize how many answers you should have in here. So I'm going to have 2 rows and 2 columns. So essentially I'm going to have 4 elements answers in there. So if you remember what we said? We said run and dive, row by column. So this first answer is going to be, 2 by 1 plus 3 times 0. And if we tidy that up, that'd be 2 plus 0, which is 2. Then if we go and do the next one, so we've got row 1, column 2. That one would be 1 times 0 plus, 3 times 1. So that would be 0 plus 3. That gives 3. And then let's go do the next one. So I'm going to go row 2, column 1. And I'd get 1 times 1 plus 4 times 0. So that would be 1. And the very last one, if I go second row, second column, that will give me 1 times 0 plus 4 times 1. So which ends up being 4. Now, does this look like matrix A? Yes? So can you see timesing something by the identity matrix is going to give the same one back. Did you see that? It's like timesing it by a number 1. So really, it doesn't matter if it's at the front or see how this one, the identity's at the front, it won't matter. So if I saw that, I'm not even going to worry about doing that manual multiplication. I was just doing that with you to practice that technique. But if I saw this question, I'd quickly just write out A, because I know timesing something by an identity just gives the same matrix back. So why do we need it? We need it because sometimes we use the identity matrix to solve problems, because you can times it by it and it doesn't change the value. Can you see that? If you times something by 1, you're not really changing the value. But sometimes we need it to be able to do some operations. So if you're, and this is probably what we need later on. So now we're going to look at the inverse of a matrix. But first we're going to look at what is the inverse. If you're asked to get the inverse of 3, what that means is it's like you get the reciprocal of it. So really the inverse of 3 is 1 over 3. Yeah? So 3 times 1 over 3, doesn't that give, that'll give us 1. Yeah? Timesing anything by its reciprocal. So say I had 4 and I times it by its reciprocal or its inverse. Yeah? You'll get 1, won't you? Yes? So sometimes we could say x times 1 over x. That's also going to give 1, isn't it? But we could also write that. Can't we write 1 over x? Can that be written like this? Doesn't that mean the same thing? Yeah, equals 1. So this is sort of the way you can, that's like an inverse. You can say something to the power of a -1 is its inverse. Okay, so we are going to need to use the inverse to use in matrices. Okay, so you need this as well. So the inverse actually is when you get your matrix and you actually raise it to the power of -1. That's how you find it on your calculator. But can you see, if you're timesing something by its inverse, look up here, can you see it's a way of dividing? Would you not agree? Like if you see here 4 and I times it by 1/4, isn't that the same as saying dividing by 4? Do you not agree? Yeah? So in matrices, when we're trying to solve, say, a problem, say I had matrix A times matrix B equaled an answer. So I'll just say AB like that, okay? Say I had that problem. Say you knew this, you were given this, and you were given that, okay? So if you were thinking just like algebra, if you were trying to find B by itself, wouldn't you move this over an equal sign? Yes? And wouldn't it do the opposite, which is dividing? Is that true? Yeah. Yeah. So in matrices, we can't use the function of dividing. What you have to do is you actually have to use the inverse. So you, instead of dividing, you put that in your calculator, the inverse, and you times it out. So we can't really use the function of divide in matrices. We have to use this inverse, the thing to the power of negative. So that's why we're going to learn now how to work out this inverse matrix manually. So you've got a formula here of how to find the inverse matrix. So this is if you've got a 2 by 2, and that's the only one you're ever going to get asked manually. So if you look here, we've got matrix A, and it has its 4 elements A, B, C, and D. So you would have numbers or something there. The way you get the inverse is you follow this rule up here. So can you see what you're actually doing is you swap those numbers around, you make these ones negative, and then you also have to put times it by 1 over this determinant. So therefore, what's the determinant? There's the rule of how you find the determinant. So what you're going to do is you're going to take this A number and times it by the D, and you'll take C and D, and then you'll get a number. So let's practice it to help you. So first of all, down here, they're asking me to find the determinant. So the determinant rule is you do the AD like that. So in this instant, A is 2, so I do 2 times D, which is 5, minus, then it'll be 3 times 3. So what would that be? That would be 10 minus 9 equals 1. Okay? You got that? That's how you find the determinant of a 2 by 2. You do the A spot times the D spot minus the C times the B times C. All right, now they want me to find the inverse of matrix A. So what I have to do, I'm going to use this rule. So I'm going to say 1 over the determinant, which is 1, and then I'm going to times it by. Now I'm going to swap the two numbers. So the D1 comes up here, the A1 goes down there, and I'm going to make the B1 negative and the C1 negative. What happens if it was already a negative number? What do you think happens? It becomes a positive. Good. Now, if I've got 1 outside and I times everything by 1 on the inside, remember scalar multiplication, it just remains the same, doesn't it, in this case? If it was a number, we'd have to change it, but this one was easy. It was a 1. Okay? So you're just going to practice doing basic ones of these, and I'm pretty sure that is what these little questions here today are. So this is a good one for both general kids in year 11 as well as methods. It's going to help both of you. This is covered in both. So everyone could give this a go today.